All right, here we go. Let's talk about 1.15. All right, today's lesson is all about linear exponential change or exponential growth. Okay, you have seen this before in your previous classes. Realize it or not, it definitely has happened already. All right, read that. I want you to pause here, read the question over, read that first explore. All right, so it talks about Twitter's number of tweets in billions per year. Write a sentence explaining how the sequence of events changing within the context given. Sequences are rarely perfectly arithmetic or geometric, but it's useful to consider that. All right. Well, we skipped the section about arithmetic and geometric, but that's because you've seen it before. Okay, and we'll continue on. All right. First thing I want to say, it says, at year, this is the over 6-month period. The number of tweets in the billions were this month, were this many. Okay, so down. In month 0, it was 8.4, 2, 9.26, 9.72, and 10.21. Okay. So now I want you to decide, okay, what type of increase is this? Is it going up by, are these numbers, obviously this is going up by 1 every single time, right? This left side, 0, 1, 2, 3, 4, 5. Okay. Are we increasing by the same amount every time over here on the right-hand side in our number of tweets? I'm going from up 0.4, but I don't go up 0.4 here, I don't go up 0.4 there. It's pretty close, but it's not exact. So we want to figure out, okay, how much the number of tweets are increasing approximately each month, okay, percentage-wise. Well, if I do this, I divide 8.4 by 8, I get 1.05. If I divide 8.82 by 8.4, I get 1.05. So this number is over 1, right? This is a review from our last section. It's over 1, so that tells us that there is a percent increase. All right, that percent increase, okay, is 5%. So that's what I would say. Number of tweets increased approximately 5% per month. So I'm going to write that down. Number of tweets increased by about 5% each. Whether the sequence is arithmetic or geometric or neither. Well, technically, since it's not a there's not a common difference, this would be a geometric sequence. And remember from our last section how we chose to write that, how we chose to write like a general term here. I take my first term, which is 8, and multiply it by the percent increase, 5, some number. So it's 1.05 to the n, and then times 8. So 1.05 to the first power, and then times 8. This number comes from here. This number comes from our first term. All right. Next one. Suppose the number of Google Plus users in millions per month over a 6-month period were as listed. All right. So I'm going to pause that and fill in my table here. All right. So here we still see that increase of 1 on the left side in our months. That makes sense. Here, if you recognize, okay, obviously I'm decreasing. My value is decreasing. Is it decreasing at a constant rate? Okay, so if I go from 3.8 and I subtract 3.8 minus 3.68, this goes down minus 0.12. I do the same thing, 3.68 minus this, I get minus 0.12. All right, so I'm decreasing every single time by negative 0.12. So this is going to be arithmetic because there's a common difference. All right, that means it's going to be linear. All right, this is going to connect to our linear. Okay, so how do we start with that? We'd write our first term, 3.8, minus our common difference, 12 times n. Okay. What does that mean within the context of the problem? It means a number of users decreased by 0.12 million or 120,000. All right. So today we're talking all about linear and exponential change. Can we determine if a function is linear, exponential, or neither from a graph or table or scenario? How do we relate arithmetic and geometric to exponential? We'll talk about that as we go along. Just know that which arithmetic is linear and geometric is exponential. If a graph appears to show a linear exponential chain, is it enough to conclude that it does? That question makes zero sense to me. But let's keep going. All right, a function. All right, remember, functions. It's a rule that assigns an independent variable known as the input to exactly one output, all right, or dependent variable. We say that a dependent variable is a function of the dependent variable. All right, remember that for every x, there's only one y. That's basically what we're saying. Okay. So, for example, if we talk about, here's an example of a linear function. All right. Here's an example of the table and the example of a graph down here. All right. You can look that over if you would like. We're going to keep going. Let's talk about example 1 here. Okay. We're talking about the owner of a new company. All right. And yada, yada, yada. Go ahead and read that over. All right, so we can see by looking at our table, obviously this is increasing by 1 every single time. I can also see that on the right-hand side, the total number of customers is increasing by 500 every single time. Okay, so that would tell me that the sequence, all right, if I start at 0, this is my starting point here, it's technically 0 plus whatever my rate is, 500 times n. Okay, because it is linear, I just add, all right, like the sequence for the nth term, like it says down here, is technically 0 plus 500n. On the graph, we can see that our graph is increasing at a constant rate. So linear function, we all are aware of what a linear function is. Linear functions are this, ladies and gentlemen, y equals mx plus b. Now, obviously, we may not have these actual letters in our equations from here on out, but that's what they mean, okay? It all means the same thing. Okay, they're all talking about look, here it is. The equations of linear function have the form of our dependent variable, which is y usually, plus our starting value, which is usually our b, okay? And plus the rate of change times the independent variable, all right? That's literally what y equals mx plus b is, okay? So let's look at an example, all right? And do it ourselves, okay? So how am I going to do this? Okay, so we want to think about, first off, I want to think about what my starting value is. My starting value is negative 18. That's important to know. I'm going to back pocket that, all right? What am I increasing by every single time? I'm going up by 1. It's a constant change here. That's good. What's happening here? I am going every single time. I'm actually going up 6, up 6, up 6. So my rate is 6. All right. My rate is 6. My starting value is negative 18. So it's going to be y equals negative 18 plus 6x. All right. It's x and y because that's what the table used. Okay. There may be tables that don't use x and y, in which case we'll use those letters that they give us. Now, it still technically means the same thing. X is our independent, y is our dependent. So if we look at this second example, m is our independent, a is our dependent. All right. It says you have an interest fee loan of $800. You're paying it off at a rate that's very important here of $50 a month. Model the situation with the table and graph the equation. Is it linear? How many months would it take you to repay the loan? So at month 0, I owe $800. I pay it off $50 a month. So then I owe $750, and then I owe $700. And then I owe $650, and then I owe $600, and then I owe $550. All right, so the amount I owe is decreasing by $50 a month. and the number of months just going up by 1 every single time. So let's use our letters. Our dependent variable, which is here, is A. Remember, our dependent variable here was Y, so it became there. So this is going to be A equals. Our starting value here was negative 18, so I wrote that first. Our starting value here is 800, so I'll write 800. What is happening with my, what is my rate? I'm paying it off $50 a month, which means the amount that I owe is decreasing by $50 a month. When I pay something off, obviously we can see this is going down. Going down, I'll write that. Okay, it's minus 50. That's a 5. Minus 50. Minus 50. So that means I should have minus 50 times my independent variable, which is M. Okay? Let's maybe change gears a little bit and talk about example 2. All right, we've talked all about linear, so now we're going to talk exponential. All right, here we go. Hopefully you took a minute to read this. This is talking about a virus. Okay, let me make something clear here. Okay, this book was written prior to 2020, prior to 2019, when before this global pandemic started. So I don't want you to think that I'm trying to infuse my views about what's going on in our world today by the types of problems that we do. All right, a lot of times in math, you see problems about viruses or about flus because of their exponential growth. Okay. This is not some sort of political statement. I want to make that very, very clear. All right. Having said all that, let's take a look at this problem. Here we go. So it said that, what does it say here? I should read this over myself. The virus tracked by 100 people, each of whom infects 2 more people on the first day, and after which they're no longer contagious. Write a function model. Assuming the infection is continuing to spread to a sick person to 2 additional people. So patient 0 is going to infect 2 people. From there, those people will infect 2 people. From there, each of those people will infect 2 people. Okay. If we look at the whatever you call it, the table. This is called a table. If we look at the table, all right, we can see that obviously our days are increasing by 1, and our dependent variables, our dependent values, are not increasing at a constant rate. Instead, they are doubling every single day. All right, they're doubling every single day. So if they're doubling, that is a rate. Okay, obviously the last one was a rate, but this is a common difference, we call it. Okay, if I divide 3,200 by 1,600, I'll get 2. If I divide 1,600 by 800, I'll get 2, and so on and so forth. That is a common, not a common difference, a common ratio. I apologize for that. A ratio is 2. All right, you can see by looking at the graph that this is exponential because it jumps up in a hurry. Okay, obviously linear would be a straight line. Exponential is a curve. It gives you all this more information about this. Remember, it's always going to start off with the starting value times the common ratio. So exactly what I was talking about here. Here's our general thing. Okay, there's exponential functions. We can have growth or decay. All right. I always, when expressing our exponential functions, it's our starting value and times our multiplier to our independent variable. It's very similar to linear functions, except that we're using multiplication instead of addition or subtraction. Okay. All right, so let's take a look at this. All right, so we're going to look at 2 different approaches here on this one. Okay, it says a company wants to project growth using both linear and exponential change to see long-term effects. The company begins with 150 clients. The CEO, we are doing 2 things. We are comparing 15 clients per month versus a 10% growth. All right, 15 clients per month. Adding 15 clients a month is going to be linear because I'm just continuing to add 15. So what would that look like? All right, so that would look like y y equals, I start at 150 plus 15 clients per month, where n is the number of months. Okay. If I wanted to reach 500, I would say, okay, 500 equals 150 plus 15n. Subtract 150. That's 350. Plus America, I got better odds. Equals n. So then n would equal, I got 23.333 third months. Okay. I want to approach it from a 10% growth. 10% growth means that I'll have y equals 150 times 10% increase each month, 1.10 to the n. Okay. How long would it take to reach 500? Well, we can do this two ways. I can use logs to help me solve, and I know once I say that, you all are going to freak out a little bit, so I don't necessarily want to use logs. What I would recommend for now, until we review our log properties, is to guess and check. Unfortunately, I would start off with 1, then 2, then 3. Okay, but be careful how you plug this in. All right, be careful how you plug this in. Make sure you're using parentheses like this and to the end and to the like whatever. I got n to be 13 months. So which one is quicker? The 10% growth is quicker to reach 500 clients. Holy buckets! Here we go. Take a second to read that over. All right, so what I want us to do is I just want to write these functions. I want to write the function, and we'll worry about the 200,000 later. These functions, all right, population increases by 5,000 residents per year. That's a rate. Okay, that's staying consistent every single year. We're increasing 5,000. All right, so that's going to be something like y equals, what's my starting population? Residents plus 5,000 x or n, whatever you want to do. Okay, use that to try to set up an expression for b. All right, go ahead and try. Okay, hopefully you recognize that still it's going to be 100,000 plus, because we're increasing, but now we should have 8,500x. Population increases by 2.5% per year. Now we're talking about exponential because it's a percentage. So still I'm going to start at 100,000 people and times 1.025 is the x. Why is it more than 1? Because it's an increase. If it were a decrease, I would subtract whatever this percentage was from 1. Try to come up with the equation for the part D. Here we go. Y equals, hopefully you recognize it's still 100,000 because that's our starting population. And we're going 1.03 this time. All right. We're going to circle back to the 200,000 part, but that should be it. What's the point and what do we learn? We talked about modeling change with linear and exponential. And we connected that to arithmetic. All right, that's it for today. Adios.